Alrighty, folks, so we've gone through the basics of momentum and impulse, and we even looked at some examples of simple collisions, either bouncing balls off of each other or off of a wall, and cases where we used bouncy balls and mud balls. And hopefully through that process you've gotten familiar with the basics of momentum and impulse. Now let's take some time to look at a couple of more detailed examples that might be more typical of, say, homework problems or test problems. So this example is one of my favorites. This is the home run example. It's a baseball example. Now, I'm not a huge fan of baseball myself. I'm more of a basketball and football guy. But nonetheless, this is a fun, simple example that I think everyone can at least imagine. Everyone's familiar with a home run. You hit the ball out of the park. So the problem reads like this. A pitcher throws a baseball with a mass of 145 grams at a velocity of 40 meters per second, which is about 90 miles per hour, pretty typical for a major league pitch. The batter cracks it out of the park with a velocity of negative 50 meters per second. It's going in the opposite direction that the pitch was thrown in. And that would be about 110 miles per hour. Reasonable for a home run ball. The bat makes contact with the ball for only 0.7 milliseconds, less than a thousandth of a second. Now, during that time, how much force acts on the ball? Now, these are tricky problems like this one, because they're going to require us to connect some dots between the different definitions of impulse. So if we were to just start drawing up our solution, we would always start with writing down all of the known and unknown information. That's what I always encourage my students to do. So as we read through the problem, first we see we're given a mass. But there is a trick to that mass. That mass is in grams. 145 grams. Now, kilogram is the standard unit. Remember, kilogram is part of the definition of the Newton. Kilogram is part of the definition of the joule. We typically use kilograms for momentum, though it's not required. But if you're going to have forces involved, it's going to need to be in kilograms. So the first thing we need to do, as soon as we write this value down, 145 grams, I'm going to convert it to kilograms. 0.145 kilograms is what that mass should be. We're given an initial velocity. That ball is thrown at 40 meters per second. We're then given a final velocity. It's struck by the bat, and then its velocity is negative 50 meters per second. We're then given a time. This time is also in some unique units. It's in milliseconds, so we can convert that back to seconds. Seconds, after all, are part of velocity. They're part of the Newton. They're part of the joule. Seconds are our fundamental time unit. So we need to change 0.7 milliseconds into 0.0007 seconds. We need to move that decimal place 3 times. And then we're asked for a force. Now, there's a lot of information here that covers a lot of bases, no pun intended. We've got mass, we've got 2 different velocities, we've got a time, we've got a force. And if you're left to think about what equation to use to solve this, you might be stumped. You might look at several different options. Is it something out of chapter 3 that there's forces involved? Or is it constant acceleration? We've got an initial and a final velocity. Well, there are several ways you might approach it, but obviously there's going to be one way that works and a lot of ways that don't. And what I would focus on in problems like this is being packaged a force and a time together. When we talk about forces being applied for a certain amount of time, that sounds a lot like the definition of impulse. So when you see forces packaged together with times, you should think impulse. How hard I push on something for how long tells me how I change its motion or how I change its momentum specifically. But impulse has 2 definitions. Impulse is, at its core defined as change in momentum. But we also looked at how impulse could be computed with forces, that impulse could be force times time. If we rewrite this as force times time equals I, we can see Ft equals I also equals delta P. And by the transitive property, that means that Ft equals delta P. We've sort of created a new formula here. We've created a new equation. Ft equals delta P. Really, that's just saying that I equals I. And I'm sure you all would agree with that. I certainly equals I. If we just change the two definitions out, force times time equals change in momentum. So this is our equation we'll be using to solve this problem. And I might actually write this on your equation sheet as a sort of special case whenever we connect the dots between these two definitions of impulse. And there's a lot that can be done with this equation. Particularly, we can solve problems like this. We can look at how, when you apply a force to something, it changes the momentum. Now, in this problem, we were asked to come up with how much force was acting on the ball. So if we want to solve for F, we need to divide by that t that's multiplying it. And we can see that the force is given by the change in momentum over time, or rather mv final minus mv initial all over t. And there's a few things when we rearrange this equation like this that I like to point out. The amount of force is inversely proportional to the time. The time is on the bottom. That means if we can increase the amount of time, we decrease the force. Or the other way around, if we decrease the time, we increase the force. That is what it means to be inversely proportional. But let's focus on that first way I phrase this. If we can increase the time, we can decrease the force. This is why we have airbags. This is why you should bend your knees whenever you jump, or when you jump off of something and land. If you can stretch out the amount of time during an impact, you decrease the amount of force. However, in this problem, that time is pretty small. We have a very, very small time that this ball is being struck by the bat. So if we have a small time, we can expect there to be a big force. So let's plug in our numbers. We know that the mass is 145 grams. We converted that to 0.145 kilograms. So 0.145 kilograms, our final velocity, mass again, our initial velocity, and we divide it by that time in seconds. And when we do all of that, we see that the force ends up being negative 18,643 newtons. Those newtons, if we follow along, up top we have kilogram meters per second. On the bottom we have seconds. That is kilogram meter per second, or kilogram meter per second squared. That is the definition of the Newton. Sure enough, we do get units of force. But we get quite a large force, and that is because it was a very small time. We also see that it's negative, and that makes sense. The force is applied in the negative direction. That is the direction the ball ends up traveling. It came in the positive direction, it left the park in the negative direction. So if you're going to give it a good smack to smack it out of the park, in this problem, that direction was negative. The force applied to change its momentum would also be negative. But this is a great example. I love putting these two equations together. It really is a beautiful thing, and this is sort of getting at the bigger picture of physics, finding connections between different variables and recasting them to make new equations. So don't be surprised if you see this again. I will almost certainly sneak one of these problems onto the test. And when I say sneak, I'm not going to do anything sneaky. But you do need to remember, if you see a force packaged with a time, you're likely using impulse as force times time. All right, we'll be back with one more example from this chapter. Let's look at an example of recoil, another good application of conservation of momentum. See you then.